I think there's several sides to it. One, which is historically the first, is just the fact that we have a theory due to Einstein, now 100 years old, which postulates objects where light cannot escape. This is very natural once you accept that speed of light is the fastest one can communicate, and then you combine this with gravity, as Einstein did, to construct, if you like, in your mind, a theoretical object which has such a strong gravity that escaping from it would mean you would have to travel the speed of light. So there you go, that's your black hole. So in that sense, this is a 100-year-old prediction of a otherwise perfectly proven theory, which has been considered one of the cornerstones of theoretical physics and human ingenuity. And so we would like to test that. We would like to see whether the universe has actually taken advantage of general relativity, so to speak, and produced objects which follow this. And that then leads us to, if you like, searching for these objects, exploring the universe, and seeing whether these things exist. And there, indeed, the story is, took about 50 to 70 years to get the first, if you like, inklings that they might. And now we have, I would say, pretty solid evidence that they do exist. That's part one. Part one is then, why does the universe use them? And do they have any role to play in the universe? And that too, we've been exploring, and we are seeing, the massive black holes, for instance, in the centers of Milky Ways have been exceedingly important for controlling, if you like, how massive galaxies could grow too. Well, I mean, I think the story with black holes is that they're not invisible, as you might think. I mean, they are black in the sense that no light, no other communication can escape from them. But when you have material falling into a black hole, on its way to disappearing behind the so-called event horizon, it becomes, it converts gravitational energy into heat and radiation. And so actually, in many cases, you can see this very intense radiation in galactic nuclei, but also in stellar systems. And these are the candidates, if you like, where you might want to look. But in the end, gravity you can make visible through its action on other objects in the vicinity. That's the point of the theory of Einstein, is matter changes the curvature of space-time for any other object in there. And the obvious case we have in our mind is the planetary system. We have the sun, and we have the planets orbiting on almost circular orbits around them. And the fact that the orbital speed increases inward is exactly what you would expect if there's a dominant mass at the center. And that is true whether or not you switch on the sun. So switch it off in your mind, do the same thing, and you have to infer from the motions of the planets that there's a sun in the center, it's one solar mass, it's very compact. And that kind of measurement we've been undertaking in the center of our own galaxy, but also other galaxies, with sufficiently high precision, and also coming as close as you can to exclude other possibilities. And I would say, certainly in our galactic center, we've now come to a point where nothing else fits in there other than a black hole. If you take this as sort of a one-time, very strong golden proof, and then you accept that in essentially all other cases you won't get to that accuracy individually, but you see the same kind of phenomenon, yes, then you can say now that probably every or most massive galactic systems have such a black hole in their center. Indeed, that's been, I would say, the core of studies of many, many astronomers. And there we take advantage of the fact that we have a time machine in astronomy. Again, the fact that speed of light is finite means that as we look out in space, the further we look out, the more we look back in time. And so we can actually, with the big telescopes in space, but also on the ground, see objects like our Milky Way, but now 10 billion years ago. And there we can study, so to speak, how this system, Milky Way system with many stars, gas, plus a central black hole evolved over time. And what we find, remarkably, that as we go back in time, a Milky Way like ours was much, much more active in forming new stars. I mean, nowadays our big Milky Way system with hundreds of billions of stars forms one sun per year more. That's nothing. Back then, it was 100 times more. That's because in the early parts of the universe, there was much more gas around between the stars, which lead to star formation. And at the same time, that gas could also be funneled into the centers of galaxies where it formed black holes. Once the black holes formed and accreted, they started spewing out energy at enormous efficiency, and that stopped further star formation in some systems by ejecting gas. And so it's sort of a symbiosis of this central object forming at the same time and yet then acting on the system as it evolves. That's right, a very fundamental role, and we are still exploring exactly how fundamental it was. We also are exploring, of course, how much at the same time it was. I mean, could it be that the galaxies formed first, so to speak, a little earlier, and then the black hole, and then they stopped the growth? Or was it that the black holes were first? Could it be that some black holes actually were present already at times where there were no galaxies? That means they were actually formed in the Big Bang. These are all questions which need to be fully solved, but certainly they played a major role. Well, it certainly tells us, other than that it's there, which is sort of the physics part of it. One of the things which you learn there over the years, and I've been at it now for 30 years here, with ever better instrumentation, ever better new techniques and so forth, is that much of what we thought was true in the sense of predictions, expectations, turned out to be wrong. So for instance, one of the obvious things you can think about is what happens to the region around black holes in terms of other stars. And you will very quickly come to the conclusion that you cannot have any further formation of stars near a black hole. Why? Well, star formation happens from thin interstellar gas in our Milky Way and in other galaxies. So basically, very thinly distributed stuff then starts to shrink into a cloud, which becomes denser and denser. And then at some point, it falls together and forms a star, starts producing fusion, hydrogen to helium and so forth. And that's star formation. Well, if you now have a black hole nearby, then the gas initially will see that black hole and then not itself. It cannot fall together. Absolutely impossible. Yet comes the observational fact, the center of the Milky Way around that black hole is one of the most rich and powerful star-forming regions in the Milky Way. What have we not understood here? Is it not obvious that they cannot form? Has somebody brought them in there, or what? And so these kind of things you can find in multiple forms that we just were surprised by looking very carefully in this region by what would happen. And once you understand it, of course, surprises always lead to more understanding. I mean, they lead to more surprises perhaps, but certainly at some point you will understand why there was star formation. I think we do. But then once you know this, you can apply this to other systems where you don't have the detail, like in external galaxies and very distant objects and so forth. The answer is it's at about the lowest scale a black hole can perform at. In the so-called quasar systems, where you have typically 100 million solar mass black hole, the high state, that is the most energetic production of energy, happens when these guys eat 10 stars per year. 10 suns per year. So at that level, our black hole in the galactic center is sort of at the level of a nano performance of this. So why is that? Well, the reason is pretty damn obvious, really, in the end, which is like many things in astronomy. Gravity is always trying to pull things together inward. And what keeps things out is the conservation of angular momentum. So once you have things, in orbit around something, in order to fall inwards, you have to take away the swing of the angular momentum. And for a piece of gas in the Milky Way to fall into the black hole in the galactic center, you have to remove all but 10 to the minus 9 of its original angular momentum. And that's the trick. That's the difficulty. And that's why you have to really go to extreme ideas, which nature then comes up with, to be able to accomplish this. And this does not happen for most black holes. So most black holes nowadays are in the sleepy state. An asteroid per day is not going to change their mass, and it's not going to change much their radiation. A little bit of X-rays, a little bit of infrared, a little bit of radio, but nothing very, very spectacular. But sometimes, or in the early universe, you get much more effective transport of angular momentum, and then material can come in, and then you can see this spectacular phenomena. Some of the things are absolutely, standard textbook knowledge and fully what we expect. In fact, the spaghettification, for instance, we currently are seeing a little cloud of about 3 Earth masses of gas, which we started observing about 10 years ago, getting spaghettified in the galactic center, because unfortunately that cloud was mostly going right into the black hole, almost as fully aimed at the black hole, being drawn out into a long spaghetti, and now coming back out and actually pulling back together again, something which you would expect. Other things in the movies, I would say, are certainly allowable extensions of the mathematics. For instance, the idea of wormholes. But I would say the prescription in the fine print, which Kip Thorne would give you as a physicist, not as a mathematician, would be don't use unless you want to expire, because these mathematical solutions are really only that. They likely are, almost certainly, are not usable for actual experimentation. Can happen, could happen, but that is, so to speak, the formal relativity lingo on this is without dust. Dust is, so to speak, these solutions of space-time are done without any material. So you only, you inject, so to speak, the space-time as such, and you construct your solution. But then if you put something in there, so to speak, to test out what happens to that something as it goes through this, the solution collapses. And so it's a really purely mathematical solution. Not only theoretically, that's actually significantly part of special relativity. You don't need general relativity for that. And that's been tested in many experiments on Earth. I mean, the lifetime, for instance, of unstable cosmic ray particles coming into the atmosphere. I mean, this was one of the first spectacular tests of the time dilation and so forth effect. So I think that's all, would say, clear. The famous effects of acceleration, free fall, all of this, I think there's absolutely no question about it. Yeah, in principle, sure. Yeah, no, that's fine. I mean, I think there's always the question to what extent such type of experiments can be really executed and where it might break down in practice. But no, in principle, yeah, sure. It's just once you start, so to speak, manipulating your experiments or your movie, going really into the region of black holes, then it becomes highly questionable. Well, in a normal black hole, yeah, you're done. I mean, there is no other solution other than the infalling observer coming to the singularity in finite travel time. I mean, that's very clear. You will end up in the center, and then, according to general relativity, the density in the center is infinite. And sorry, I mean, you've had it. But I mean, the wormhole scenario, of course, is a solution in some coordinates of the problem where you can construct a solution which is not like that, and so that was the question. It was not an ordinary black hole, I believe, they were trying to travel into. I don't see how this would work, no, because let's start with the simple part, which is let's be very practical. Okay, we had the lunar landing, okay, and since then what? We now have ionic propulsion, which has been tested, so we in principle have speeds, rocket speeds or transportation speeds faster than just chemical things. Still, we haven't really used that for human transportation. We've been talking about Mars experiments, and so I'm getting stuck here at a much lower level than these conceptual things. I mean, I would have to say we would have to solve so many practical problems. How do astronauts survive in normal, even solar system-like environments? I mean, I don't know whether you know how close a call it was for many of the lunar experiments in terms of the lives of the asteroids, because there were solar storms sometimes between, just close to these early experiments. If they had occurred during the mission, the astronauts would have been killed in action. So in that sense, I apologize that I cannot, this is so much of a practical endeavor where humanity would have to expend so much of its energy to get to the lowest levels of this, namely traveling at fully engineerable, I would say, speeds and so forth in interstellar space, which we haven't mastered because it's much too expensive. I think it's not a non-trivial question. As a scientist who would like to primarily understand, the world and then perhaps experiment if need be, etc., I would say no, we don't need this, because the sophistication of robotry we have now in space is plenty enough. I mean, the complexity of the telescopes we have out there, or of the Mars missions without humans, is astounding, and can certainly be certainly we can do more. Other than the money, again, I mean, just think of we have seen a very successful European mission, Rosetta, whose next stage obviously is a return mission. Yet that thing makes this mission so expensive that it's highly unlikely that Europe can carry it out. So in that sense, that's my first thing, is that let's be real here. How much money are we willing to spend? The landing on the moon was possible only at the effective cost of, I don't know, hundreds of billions of current dollars or whatever it was, because there was the Cold War. And I guess that is where I would say, as a scientist, one has to accept that even if you think you know how one can do it more efficiently and better and so forth, you may have to wait until an occasion like this comes where something happens, where something gets done, and you can sort of ride on that train, if you like. So science certainly has had a good seat. Space science certainly has had a good seat on the train of the Cold War, and likewise, I mean, sure, it's clear that it's much more spectacular for the public to see an astronaut land than just one of these little robots. But what happens if the astronaut dies? See, I mean, we've seen that too. We've seen that all of a sudden a program which was in full swing at NASA was questioned immediately, full blame, the Challenger, stopped everything. And so I would say all these things are, they don't happen in this hyperspace of imagination. They happen in real space where things which seem to be attractive one day politically are not possible the next day. Yeah. Well, let me say that although I'm personally not engaged in this, there's no doubt that this research area in astronomy will perhaps be the dominant area of astronomy for the next 100 years, and it will blossom to enormous extents, which are fully justified. I mean, this is and highly interesting. It is obviously immediately the connection to the solar system comes in, and this hangs together. And for people doing the research in many wonderful ways, I think there's no doubt it captures the imagination of the public. I no doubt. Now, it's clear at the speed we are going that there is one direction of research where you basically now are trying to understand why it is, which you never assumed, that the solar system of all places is one of the weird places, and not the common example of everything else. So that's the demographics of planetary systems, which is happening right now. That's maybe not as spectacular, but it's very important to understand what systems are there, how are they realized, how warm are the planets, is silicon chemistry or is oxygen chemistry possible? Are there other chemistries, etc., etc.? And that will be happening. Naturally, one of the steps there will be chemical analysis of atmospheres of planets, and that's happening already in some of the big things. Sometimes spectacular results already, and they will get more and more sophisticated towards looking at more the water world types, lower mass planets. Further away from the planet, which are in the in the area where, in the distance temperature region where life could exist. And then I'm fairly certain, this chemical evaluations will let us allow to look for non-equilibrium chemistries. Maybe not uniquely so, but I think that will be the case. Now, we are still far away from your question, okay? I'm telling you what, I'm sure this will happen within the next 20 years. Absolutely, absolutely. It's just a question of money, and in fact, we've seen ingenuity come to the help. The so-called Kepler mission, which has taken one way of detecting these planets, namely by basically occultation of systems which are age-on, which are rare. Why would you do that? Have been incredibly fertile in terms of demographics. We have thousands of planets now, and very well studied. So I have no doubt that the chemical studies of surfaces, atmospheres of planets will come and will get ever more sophisticated. It's just a question of time and money. Then the question is, to what extent such studies can actually make a unique statement about that the non-equilibrium you might find, for instance, ozone to oxygen ratios or something like this, must be driven by an energy source like bacteria or something like this. I think that will happen, but the outcome of that I cannot be sure of. There I'm too little close to chemistry to make sure to understand whether this statement can be made. The little green man with waving their flags, no, that will not happen. Next question you could ask: can we make high enough detailed pictures of such surfaces? And again, I don't know. Maybe, and that's already the indications, many of these systems are highly hazy, so that it's sort of the kind of fly there and take pictures of like the Earth may not work. Absolutely. No, it's a very important point, extremely important, and one which we need to talk to the public about, and vice versa, all the time. And I'm sure there are many elements to the answer. Let me try to give you one on several other aspects. Aspect one, that's us. Why? Well, the other day I was walking on near a creek with my wife, who's a pediatrician, and there was a mother with a toddler, and the toddler would take one step and then topple over and sort of boom, sat there, and look, how toddlers look, a little astonished. I fell down, gravity overcame me, and so. And then all of a sudden sees a flower, face changes, cannot speak yet. Bends over, pig's flower looks at it. There it is. There's that element. That's us. We want to know. That makes us human. We want to know. The next thing is, obviously, we have extremely benefited from understanding that this curiosity we have then leads to enlightenment and knowledge, which then in the third level leads to technology. And I think, although that's not always easy to get across, you cannot jump the first two steps and only to get to the third. I mean, if you want to build a car, or let's say, if you want to build a GPS system, you better first understand general relativity, or not try first building the GPS system and drive your cars without general relativity, because then they crash into each other. I mean, that's where you have to first do the step of the basic understanding before you can do the application. Now, clearly, there will be times in a given society where that complex understanding, the basic curiosity, the wanting to know of the society, the connection of knowledge and technology and education to the well-being of the society breaks down, of course. One can only hope then that there will be another flower in nearby. Of course, there have been in our Europe a time when, for 1,000 years or more, maybe things were not as fast as they could have been, because things were politically going in a different direction. But I mean, I would hope, however, that if there are streams in our society, and they do exist even in countries like the US, unfortunately, exactly in the US, where people deny that there is this connection between us and our daily living and how well we live, with this basic understanding, that we have good arguments to fight it. But of course, sometimes if you might not be able to fight it. That is terrible.